So there's a really fundamental shift happening in the automotive battery world. And between now and 2026, the game is no longer just a straight up race for maximum performance. It's become this complex, multivariable balancing act. All right, let's dive right in. Here's how we're going to break this down. First, we'll lay out the new rules of the game. Then we'll get into the chemistry battleground. And after that, the paradox of structural integration. From there, we'll cover the life cycle imperative, which you just can't ignore. And finally, we'll wrap it all up with an actionable engineering playbook for 2026.
Okay, so let's start with the big picture, the strategic landscape. The core objective for pretty much every automotive engineer has totally changed. We've gone from chasing a single goal to solving a really complex equation with multiple and often competing variables.
For the better part of a decade, the mission was really simple. The number one engineering driver was squeezing every last mile out of a single charge. Maximum range. That was king, no question. Well, that era is over. The new goal is all about maximizing total lifecycle value. And what that means is that things like sustainability, cost, and serviceability, they're now top-tier engineering parameters, right up there with performance and energy density. To really get this shift, you have to understand the competitive pressure cooker we're all in. I mean, by 2025, just two companies, CATL and BYD, are going to control over 55% of the entire global market. And their dominance isn't just about being big. It's about how they've mastered integrating low-cost LFP chemistry into really high-performance packs. That has completely rewritten the cost-performance curve for everyone.
This new reality creates this just immense cost pressure. We're seeing the average pack price fall to about $108 per kilowatt hour. And get this, LFP cells in China are already dropping below the $50 mark. At prices like that, every single design choice, every gram of material becomes absolutely critical to your bottom line. There's just no room for error anymore.
So let's see how this all plays out at the chemical level. The future isn't about one single chemistry winning it all. It's really about a strategic portfolio, deploying the right chemistry for the right application to win in specific parts of the market. So the most important evolution for the mainstream right now is LMFP, or lithium manganese iron phosphate. By adding manganese, we can raise the voltage, which boosts energy density by a good 15 to 20%. And we do all that without messing with the core safety and cost benefits that make LFP so great. The big engineering puzzle here is figuring out how to stop manganese dissolution, which can shorten the battery's life, but that's a problem that's getting solved and fast. Now, beyond LFP, we have to talk about sodium-ion. Look, it's not a direct replacement for lithium, but it is a brilliant strategic tool. Sure, its energy density is a little lower, but its trump card? Phenomenal low-temperature performance. It holds on to over 90% of its capacity at minus 20 Celsius. That makes it a perfect, really cost-effective solution for smaller cars in cold climates. And that solves a major headache for consumers.
And what about solid state, the holy grail? Well, it's not some distant dream anymore. Semi-solid is already here, hitting the market in 2025 with really impressive energy density. And as you can see, the major players have laid out a pretty clear roadmap for full solid-state commercialization within the next decade. The race is definitely on.
This brings us to our third section, the huge changes in battery pack structure. And this is where we run into a really critical engineering paradox, a direct conflict between our push for extreme integration and the growing demand for repairability. The peak of this integration trend is something called cell-to-chassis, or CTC. And it's basically what it sounds like. It's where the battery cells are put directly into the vehicle's chassis, becoming a structural, load-bearing part of the car itself. Now, the reasons we're all chasing CTC are incredibly compelling. I mean, we're talking about getting rid of over 370 parts, cutting the car's weight by 10%, and boosting range by about 14%. And on top of all that, you make the chassis significantly stiffer. From a pure performance view, it's a massive leap forward. But here's the paradox. This extreme integration, which we often do with powerful structural adhesives, creates a maintenance and insurance nightmare. A minor collision, maybe some damage to the underbody, could mean the entire battery and chassis assembly has to be thrown out, which could lead to the whole car being a total loss. That's just not sustainable. So what's the solution? Well, it's coming in the form of technologies like Henkel's HEDL or debonding on demand. And the process is pretty elegant. You apply a 60-volt current to the structural adhesive, and within just a few minutes, its bond strength drops by 98%. This lets you take things apart cleanly and without destroying them. This kind of tech solves the paradox. It gives us all the benefits of integration without the serviceability nightmare. So, beyond all the technical challenges, our designs are now being shaped by these really powerful external forces. We're talking about regulatory and societal demands that have become core design parameters for every single battery engineer out there. And the speed of change, especially coming from EU regulations, is just staggering. This isn't some distant future thing. A mandatory carbon footprint declaration is required in 2025. The digital battery passport is compulsory in 2027, and by 2031, strict targets for recycled content and an 80% lithium recovery rate, they become law. Our engineering teams have to be designing for this reality today.
This regulatory pressure is forcing us to ask some pretty counterintuitive questions. For instance, could a heavier battery pack, which traditionally means lower efficiency, actually be the greener choice when you look at its entire life cycle, from cradle to grave? Well, the IAV Eco Design 2.0 concept explores exactly that. And it shows that even though steel is denser than aluminum, producing a steel housing has a carbon footprint that's 4 times lower than its aluminum counterpart. So we're consciously trading a lower manufacturing footprint for a higher mass.
And yeah, there is a direct performance trade-off. This concept pack is 75 kilograms heavier than the aluminum reference design. That's the weight penalty you have to accept in the vehicle's architecture to get all the downstream life cycle benefits.
But here is the payoff. The steel design by itself already cuts the life cycle carbon footprint by 25%. And because it's designed to be taken apart easily, its modules can be reused in second life applications. When you factor that in, the total CO2 reduction is a staggering 51%. That's right, a heavier battery cuts total emissions in half. This is the kind of systems-level thinking that's required now.
Okay, so let's bring this all together into our final section, your actionable engineering playbook for 2026. These are the key strategic moves that your teams really need to be focused on right now. First, embrace chemical pluralism. Your platforms have to be chemistry agnostic. Second, design for disassembly from day one by baking in reversible bonding. Third, prioritize data. Start building your digital twin framework now for that 2027 battery passport. Fourth, re-architect your thermal management for 800-volt systems. Things like side cooling are essential for heat management. And finally, build resilient, dual-source supply chains to navigate this complex web of global regulations. I'll leave you with this one thought. For decades, automotive engineering was all about pushing single metrics to their absolute limits. But as we've seen today, we are deep in an era of competing demands. So maybe the ultimate engineering challenge for the next decade isn't about maximization at all, but about mastering the art of the optimal compromise. Thank you.